All right, we're going to look at factoring special cases. Remember, in general, a perfect square is a number that has two factors that are going to be the same. So for example, if you have 49, 49 is a perfect square because 7 times 7 equals 49. And 7 can be multiplied by itself to get 49. So other examples would be 25 because 5 times 5. It could be 16 because 4 times 4, 144 because 12 times 12. So a perfect square is what we're going to look at for our special cases. So specifically what we want to focus on is the difference of perfect squares. So there's kind of three requirements for us to have an expression that is the difference of perfect squares. So for us to be able to use this method that I'm going to show you. The first thing that it has to do is it has to be a difference. Difference means subtraction. The next thing, if I say, okay, I want you to subtract, your question to me would be, what do you want me to subtract? What are the two things that I need to subtract? So the next requirement is that I need to have two terms. Okay. The last requirement is that they have to be perfect squares. Everything has to be a perfect square. All right, so if one out of the two things is a perfect square, no. If they're both perfect squares, but I'm adding, no. It's all of these three things, or I cannot use this method, okay? So that's why we call it a special case, because it happens, just not a lot of the time. But when it does happen, it's super easy to solve. So let's kind of look at that. The way I'm going to solve these, and you might remember these, we looked at them before, is that I'm going to take the square root of everything and then I'm going to alternate the signs. So one will get a plus and one will get a minus. And it does not matter which one happens first. So if I want to put the plus first or if I want to put the minus first. So let's see what that looks like. So if I look at this first example, I notice that I have a 1 here in front. 1 is a perfect square. X squared is a perfect square. 64 is a perfect square. So I notice that they're all perfect squares. Then I also notice that I only have two terms. And I notice that they are being subtracted. So those are the three things that I need to be able to actually factor this expression. So what I'm going to do is I'm going to take the square root. So the square root of 1 is 1. The square root of x squared is x. The square root of 64 is 8. And one gets a plus and one gets a minus. So hopefully when I did that, you're like, oh yeah, I remember this. So it should be pretty straightforward. Let's look at another one. I've got 1, x squared, and 81. They're all perfect. I've got two terms. I've got subtraction. So we're good to go. It meets all of the requirements. So I'm going to take the square root of 1x squared. Gives me 1x. Remember, I don't have to write the 1, but I could. And then the square root of 81 is 9. One gets a plus, one gets a minus. All right, so let's do this next one. 4 is a perfect square. X squared is a perfect square. 25 is a perfect square. Two terms, subtraction. We're good to go, so let's do it. The square root of the square root of 4 is 2. The square root of x squared is x. The square root of 25 is 5. One gets a plus, one gets a minus. All right, let's keep it going. Same idea here. 36, x squared, 1. They're all perfect squares. There's two terms. I've got subtraction, so I'm good to go. So let's do it. The square root of 36 is 6. The square root of x squared is x. The square root of 1 is 1. One gets plus, one gets minus. I look at the next one. Ooh, 2. That is not a perfect square. X squared is, okay, 32. Ooh, it's not a perfect square. So you're like, well, why would she put this in there? There's two terms, and I'm subtracting, but this 2 and this 32 are not perfect. Wait a second. Do you remember a long time ago when we talked about greatest common factors. Oh, here we are. So let's look at this. 2 and 32 can both divide by a 2, correct? So I'm going to now take that GCF of 2 out. So now I look and I say, okay, wait a second. 1 is perfect. X squared is perfect. 16 is perfect. So really, I have the square root of 1x is x. The square root of 16 is 4. 1 gets a plus, 1 gets a minus, but I also had that 2, that GCF from the beginning. Okay, so we add one little twist to it. So just because they're not perfect in the beginning, make sure you can't get them to be perfect by just finding a GCF. So what about this next one? I've got 2 terms. I've got subtraction. X squared, we're looking good, but 27 and 3 are not perfect. However, what if I divide both of those by a 3? That's going to give me 9x squared minus 1. Now, is 9 perfect? Yes. Is x squared perfect? Yes. Is 1 perfect? Yes. I have 2 terms and I have subtraction. Okay, now we're good to go. So I'm going to take my square root. So the square root of 9 is 3. Square root of x squared is x. Square root of 1 is 1. 1 gets a plus, 1 gets a minus, and don't forget that GCF. All right? So now we've looked at remembering about that difference of perfect squares, our special case. Now, it doesn't happen a lot, but when it does, it should be pretty nice and easy. All right, the second special case that we want to look at, still dealing with perfect squares, is called a perfect square trinomial. So again, we've got some requirements. Three requirements again. First requirement is that now it's a trinomial. So a trinomial means that there are going to be 3 terms. Okay, so I've got to have 3 terms. The next thing, again, perfect squares, just like the last one. Now, in the last one, everything had to be perfect. This one is not like that. It's the first and the last. So the A, of course, our x squared is already perfect. So our A and our C must be the perfect squares. So B doesn't really matter as far as perfect squares. Okay. Then the last requirement is that the C, the last value, must be positive. Okay. If these 3 things happen, then I'm going to factor it by a perfect square trinomial. So just like we did before, I'm going to take the square roots, but this time, again, I'm only taking the square root of A and C, all right? And then instead of alternating the signs like we did in difference of perfect squares, we're going to keep the signs the same and they are going to match B. So same signs, and I'm going to look for B to know what that sign is. Okay, so let's look at a couple examples. Okay, so the first thing I'm going to do is I'm going to make sure that it is able to be factored by perfect square trinomials. So there are 3 terms here. The A and the C are also perfect squares. The C is being added, so it is ready to say, okay, perfect square trinomials. So I'm going to now take my square roots of the A and the C. So the square root of 25 is 5x. Square root of my 4 is my 2. And I'm going to keep the sign of the B. So it's going to be plus and plus. Now, because it's a perfect square trinomial, I could have also written it as 5x plus 2 squared because it's a perfect square trinomial. So either of those ways will work. Okay? Let's look at our next one. I'm going to make sure that it works first. I've got 3 terms. My A, which is a 1, remember if there's nothing there, and my C are perfect squares. And then I am adding, so this one is perfect square trinomials. So I'm going to go ahead and take my square roots of my A and C. So the square root of 1x is, 1x squared is just 1x. The square root of 16 is 4. I'm going to match the sign of this b. So they're both going to be subtraction. So I could write it as x minus 4 times x minus 4. I could also write it as x minus 4 squared. All right? Let's look at our next one. 3 terms. Perfect square here. Perfect square here. Addition, so I'm ready to go. I'm going to take my perfect square. Perfect square of 9 is 3x. Perfect square of 64, or the square root, excuse me, of that perfect square is 8. I'm going to match the sign here. So they're both going to get plus. So my answers could be 3x plus 8 times 3x plus 8, or I could put 3x plus 8 squared. All right? Moving on. Let's see if we can do it without writing as many steps, excuse me. So I've got 3 terms, perfect square in the front, perfect square in the back, plus for my c, so I'm going to take my square root. So my square root of 100 is 10x. My square root of 1 is 1, and I'm going to match the sign of a b, so they're both going to be subtraction. All right? Hopefully we're getting the hang of it here. 3 terms again for this next one. Perfect square of 4, perfect square 121. 121 is positive, so I'm going to take my square roots, which is going to give me 2x. Take my square root of 121, which gives me 11. Match the sign of the b, so subtraction. So 2x minus 11 squared. All right? So last one. 3 terms, but oh, wait a second. 2 isn't perfect. Well, neither is 50. So you're like, why did she put this here? Oh, wait a second. Uh-oh, remember that whole idea of GCF? So 2, 20, and 50 can all divide by 2. So let's take out a 2 real quick and see what we've got. So now after we take out a 2, let's check again. I've got 3 terms still. 1 is perfect. 25 is perfect. So now it is perfect square trinomial. Again, I'm going to leave that 2. I'm going to take my square root, which gives me x. My square root of 25 gives me 5. They're going to match, so they both get a plus. I could rewrite this also as 2 with an x plus 5 squared. All right, so I just wanted to show you one where they gave a little bit of a, I don't know, kink in the plan where they gave you a GCF, but still the same idea. 3 terms, first and last term are perfect squares, last term is plus. I'm going to take my square roots and I keep the sign the same as the middle term. So those are our special cases that we want to look at. Again, both of them deal with our perfect squares. So I really kind of need to know what my perfect squares are for these special cases to work. But remember, we had difference of perfect squares where there were 2 terms with subtraction and everything was perfect squares. And then we had perfect square trinomials where we had 3 terms. The first and the last are perfect squares. The last number has to be plus. All right?